Hello, my name is Tom Zanussi. I'm a software engineer at Intel, and today I'm going to be talking about microYocto and the Internet of Things. What I'll start off with is a brief blurb about what exactly microYocto is, and then I'll spend most of the time talking about what we've actually spent most of the time working on, which is reducing static memory and dynamic memory. And then at the end, I'll actually show you how you can go get microYocto and build it and boot it on your own Galileo board if you have one. And part of that, I'll give a brief intro to two-slide intro to Yocto in case you don't know what Yocto is. And then following that, I'll talk about plans for the future, and then we'll hopefully have time for some questions. So if you go out and do a Google search for tiny distro, you'll typically find our distros that are targeting systems about, on the low end, 16 megabytes of RAM, say 256 megabytes of storage for a rootfs. And in a lot of cases, significantly more than that. And what we're talking about is something an order of magnitude smaller than that. Something, for instance, just below maybe 2 megabytes of RAM and 8 megabytes of flash for a file system, root file system. So essentially, that's what Yocto is. It's just a distro that will run that's designed to run on hardware that's that tiny. And of course, that hardware that tiny has also become synonymous with Internet of Things. And of course, the first word in Internet of Things is Internet, which means that the distro should have good support for networking, TCP/IP networking. In a lot of cases, systems this small are also single purpose. An example, running a single application, for example, IPMI application, management application. And many times there isn't a production shell, and maybe in place of that, a small web server that allows some access to the file system. So that's our target system. So how do we go about making something that small? Again, we have two big constraints, which is storage and memory. Our target's 8 megabytes of flash for storage. That doesn't sound like a lot, but in reality, it's actually quite a comfortable amount. My development system has a BusyBox shell, utilities, SSH server, web server. It's a pretty functional system, and it comes in at about 4.5 megabytes. But without much tweaking, I've actually had it down to 1.5 megabytes pretty easily. So I'm not too worried about storage, but on the other hand, memory, we're talking about something that's say 1.6 megabytes or 1.6 megabytes of RAM. That really is a tiny amount of memory, and of course that memory has to be shared between kernel and user space, and obviously, the user space gets whatever the kernel leaves behind, and so our first order of business really is to minimize kernel memory usage. As far as kernel memory usage, we can break that down into static and dynamic. Static memory is essentially the memory used by the kernel text and data. Basically, the kernel image itself. It's always in RAM. Every page taken up by the kernel static image is a page that's unusable by user space, essentially for the lifetime of the system. So obviously, we need to try to minimize static memory first. And then we have dynamic memory, which it's just as important. It's things like kmalloc, memory allocated as needed by the kernel. And of course, that memory taken by the kernel is it's just as much memory that's not usable by user space. So our other task is to minimize that as much as possible. Let's start with static memory. reducing static memory is really pretty straightforward. It essentially boils down to just removing code. Any code that you don't have building won't end up as bytes in the kernel image, and the kernel has a well-defined way of doing exactly that, which is the config system. You turn off a config option, and that code is just not part of your final image. So one of the first steps when you're building creating a new system is to essentially go through and remove all the config items that are obvious to remove, things that you obviously don't need, like device drivers, file systems, things like that. After you go through that initial process, you'll eventually reach a point where you can't remove anything more obvious, and that's when you start looking for bigger pieces of functionality that you might consider a little bit more essential, but that will give you big savings if you can possibly work around them. One example is the block layer. If you can get rid of the block layer, you can save about 200K. Of course, that means if you do that, you don't have access to block devices anymore. But for a lot of embedded systems, that's not important. You can use a file system like JFS2 that doesn't require the block layer. Another example would be print K. Print K is considered pretty essential by most people, and it is. To a certain degree, you need it to see what happens during boot. But if you can justify a way to get rid of that, you save about around 120K. But there are patches out there that will actually put print K into an init section and then discard it after boot, so it's not such a big hit. For microYocto, I didn't do that. I just turned it off, and there were actually a few things that I did need from the print K output to see for my work. And what I did in those cases was I essentially took the code that generated that text and put it behind a proc file that when I booted up, I just go read that proc file to get the same information. So I essentially did that for the things I needed, and then was able to get rid of the rest. So things like those kind of things. Essentially, you go through this step, and you'll eventually reach bottom with this too. You'll have removed all the major pieces that you possibly can, and you still realize you're not anywhere near where you need to be when you're talking about creating a small system. And that's when you start thinking of carving out pieces on your own. And that's obviously, if you do that, the best thing you want to probably be nice and put it behind a config item as well. That way, that functionality is still there. It's just configured out. You can turn it back on later if you ever need to. An example of this would be the proc file system. I turned off the proc completely, and then found that I wasn't able to boot, and that's because boot process on my system actually needed proc mounts and proc file systems just to boot. And then beyond that, there are certain utilities like PS that require the proc file system in order to function. And then there are just plain old things that you really don't want to do without, like for me, proc meminfo, for instance. So what I did was I essentially kept those essential pieces around, and I carved everything else off and put that behind a proc min configuration item, and saved about 100K by doing that. I didn't save the full 150K I would have if I just removed proc, but still that's a big win to save 100K. And then there are things like perf. Perf is a great tool, but when you're talking about trying to get a system down to, say, a text size of less than 500K or so, or even smaller, you can't really justify spending a third or more of it on perf. So it makes sense. I created a config item to remove, essentially allow perf to be toggled out, and that saved 135K. And then there are, along the same lines, there's a couple of patch sets that really were a big help. Andy Clean's Net Diet patch set, excuse me, essentially breaks up the network stack. The network stack is a huge part of the kernel. It breaks up the network stack into like 20 different options that that can be configured out, and essentially for an embedded system you can figure all of them out. And doing that saved me 200K by using that patch set. Doing that does require you change some user space at in certain cases, like for instance RT netlink. Not having that anymore forced me to get an IP address using ifconfig in the user space. And then there's Andy's other big patch set, LTO patch set. Essentially, link time optimization essentially works on optimization basically works on a per compilation unit basis. LTO allows essentially the whole kernel to be viewed as a single compilation unit, and by doing that, a more global view of the whole kernel allows for better inlining choices, etc. And combining those two patch sets together, I was able to save about 400K, which is a huge amount. Then there are just odds and ends here and there. In 3.15, there are a couple patches that remove obsolete syscalls. You can turn those off. You get 1K each. Doesn't sound like a lot, and it's not, but it all adds up. You disable a bunch of things like that, and you eventually you cut things down to the size that you need in the end. Then there are things like that haven't been submitted to the kernel, or ideas to to do similar things for different areas of the kernel. Josh Triplett actually submitted in a previous kernel x86 IO port, IO perm patch, removing that syscall, IO perm syscall that saves about 10K. So that patch set I've included in microYocto, and then there are just a couple other ideas Josh has that he may be working on, or maybe someone else will. I don't know. Removing ptrace could probably yield a huge savings, as well as and signals even. So these are just some ideas that may actually happen. So that's the basic idea behind so far that I've sort of applied to get the text size down. And here's where we actually are right now with microYocto. This is the most common use case. This is the native networking. This is the networking stack in the kernel, and then just a basic minimal functionality system, but still it's got enough functionality to be useful. Shell and utilities, BusyBox, web server, and SSH server, and all this running on a Galileo board. Essentially, the text size of that is about 750K, which is pretty good considering it includes native networking in the kernel. You can actually remove INET completely and save 150K, and not have any TCP/IP stack in the kernel, and replace that with a user space stack. An example is LWIP, lightweight internet, or lightweight IP. It's a user space replacement for the kernel stack. And it has two interfaces, the high-level interface and a low-level interface. The high-level interface is designed to allow you to basically take any off-the-shelf socket application, drop it into LWIP, rebuild, and essentially have the same functionality. The problem with that, with the high-level interface, is that it bloats everything back up to essentially where it's not worth it any longer. For instance, I had a 15K web server. When I built it was 15K using the kernel networking, and when I created the same LWIP version, it ballooned up to 105K. So I basically removed most of my gains from configuring disabling INET. LWIP does have a low-level interface, and it's basically an internal API that you need to modify your applications to use. and that doesn't carry the bloat with it, but it does require a lot more work on your part. I actually attempted to take the same web server, adapt it to the low-level interface, and at a certain point I just punted because, not that it was something I couldn't do, it's just I didn't really want to spend much time doing it, and I wanted to move on. So I didn't, but someone with more time and inclination might see this as a real, an actual useful thing to do. One particular case, in certain cases it actually would make sense to do that work, to use a low-level interface. An example would be IPMI. IPMI, like if you have a really simple network application that uses IPMI, IPMI can essentially be implemented in using 6 simple, even 4, I think, simple UDP messages. So if your application really has that level of, is really that simple, then why not just handcraft those packets instead of bringing in a whole network stack to deal with those? So that might be a case where it actually makes sense for you to spend the time to do that. And I actually did that for a proof of concept application, a TCP echo app and a UDP echo app. And I was able to, it did work, it did send packets over the wire, so it was basically functional. And when I did that, the system, the current text size was about 620K. So you can see if you're able to do that, you can actually save quite a bit just by you're already down to 600K by being able to do that. And then there are the use cases where you don't need networking at all. And in that case, you can remove all of networking, iNet, NNet, and you can remove the Ethernet driver. And the same system, when I built, after I did that, I was down to almost low 500K. So, so those are the numbers I have now. I think we can do actually quite a bit better. And in the future, I'll continue to do that. But you know, how do you actually go about improving on that? Well, you know, obviously the best way is to know the code so well that you can actually go in and just put the most expensive things behind config items and actually save your text size a huge chunk by doing that. But it requires you that you know whatever area it is that you're removing. Another option is to actually use tracing to figure out things that aren't ever going to be used and remove them. An example is I created a tool that I'll talk about a little bit later to actually trace syscalls, but also other things too. But in this case, the syscalls. And it's not really, my thing's not really showing up. But anyway, in the middle you can see what I did was I traced my microYocto, you know, in a normal, doing, you know, basically putting it through its paces a little bit, and I traced all the system calls that were used by the system, and in the middle you can see the actual system calls that were called when I did that. You can see on the left is the we're focusing here on the web server, but yeah, you know, it's tracing the whole system. But we're focusing on the web server here. We have an HTTPD and a CGI script, and these are the system calls that it actually used. It's only a snippet of the full output. And then here we have the number of times each one of those syscalls was called. So if you look at the whole output, what you find is, what I found anyway, was that nowhere is just sendfile called or splice. So if that's, the one important aspect of this is that this is a closed system. It's a single-purpose system. We're not expecting to run any application anybody throws at it. In that case, we can't really just go ahead and remove syscalls like that. But in this case, we know sysfile is never going to be called by our system, so there's no point for it to be there. Just remove it. So I actually did that, and I added a config splice and saved about 20K by doing that. And that's just an example of that same methodology we use for a lot of different things, I think. Okay, so that's static memory. Dynamic memory is just important. Dynamic memory, kmalloc, file system caches, per process things like page tables and stack and things like that. So that's what I mean by dynamic memory. You know, it's just as important as static. Any page that the kernel is using for dynamic memory is not is unavailable to user space as well. It's a little, by its very nature, it's a little harder to measure because it's always changing. It's not like you can just say size VM Linux and that's the one number that defines static memory size. The tools to do that are things like proc meminfo, slabinfo, and various tracing tools. Slabinfo is great, but it doesn't really give you an easy way to drill down into what actually contributed to the cache, to the slab activity. Tracing tools like SystemTap do allow you to do that, but they don't typically work early enough. As an example, ftrace is initialized at the end of start kernel, and by that time, there's like thousands of allocations that have already happened that it completely misses. So essentially, to sort of get around those limitations, I created something called hash triggers. Hash triggers are based on the event triggers that were pulled into 3.14 kernel. Just a little background on Linux event subsystem. Essentially, Linux has an extensive event subsystem that defines about 1,000 different events that you can actually that you can enable any one of those events, and it will log the data, event-specific data into the trace buffer, and then at the when you're done tracing, you go and look at it at the complete log. Hash triggers are similar, but instead of logging to the ftrace event buffer, what they do is hash the event into a hash table. You can look at if you can consider any you can consider each event in the each trace event as a tiny little database, set of fields that you can use any of those fields as the key or the value in a hash table. And additionally, you can also use the call chain that actually led up to the event as a key in the hash table. And what that allows you to do is essentially capture every single call chain that led to a kmalloc. So every kmalloc that ever happened, you have a fingerprint of where it came from. And here's a little more concretely what I'm talking about. Here's a trace event. This is a kmalloc event. This is the event for the kmalloc, and you can see on the left a set of fields. Any one of those can be used as a hash key or value. The ones we're particularly interested for kmalloc would be the two, not the very bottom, but the two below that, bytes requested and bytes allocated. Here's an example of an actual output from the hash triggers, early hash triggers. You can see these are two entries in the hash table. Each one of those is key using a key. They're all using the stack trace as a key. And you can see these are only two of them, but at the bottom you can see 2,550. There are actually 2,550 of those. I can only obviously show two, but that's enough for now. So if we let's look at the first one. Here we see it's a key. The stack trace is being used as a key. Here's the kmalloc event that actually caused this this event to fire. And then if we look at the bottom, we see that these are the values in the of the hash of the entry. And this happened, you can see that this happened one time. This event happened one time, and the total allocation was 96 bytes. Here's another completely separate call chain. And if you look at it's also a stack trace, it was key again. You can see that this one happened 414 times, and the total summation of those 414 times was 105K. So that's essentially what the hash trigger output looks like. And the value of this is that essentially, so we have one of those for every unique kmalloc that happened in the kernel. That essentially allows us to see what every call path that led to slab activity for kmalloc, and it allows us then go look at the code that corresponds to that call chain, and either improve it or even better remove the call chain completely. And looking at this output is actually what convinced me to go ahead and spend the time to create the config proc min config item. What I saw was a whole bunch of a lot of call chains that contain as the second to last entry proc, basically proc create, things like that. So so I figured, well, if I can get rid of most of that, I can save those call chains, and in fact that's what I did. And I saved 125 call chains by doing that. Those are call chains that are never going to be, that in this case when you turn it off, are no longer contributing to slab activity. And in the particular case of proc min, it also happened to save us 100K worth of text, but that wasn't, which is, it's a nice side effect, but it's not really the reason that I did it. It was mainly for dynamic memory reasons. So that's an example, and there's a lot more work I need to do along these lines to do more of this kind of thing. And we have the tools and the data to do that, I think. And just as a little bit of a side, it's also kind of fun. It can be kind of fun to look at this data and maybe, to me, learn things that weren't obvious to me. But when I started looking into creating a microYocto and specifically looking at what we need to do to lower dynamic memory usage, of several things I read, people who've done this before, they all assume that boot allocations are not important, that not really much happens there, and just maybe keep a counter of that. But when I actually did the early hash triggers and I looked at the data, I saw 2,500 call chains, 2,500 different allocators of just through start kernel. That by itself doesn't tell me anything. What does that compare to? Maybe a normal running system has 250,000 of them. I don't know, but it seemed like it was something that was not insignificant. And so what I did was I actually turned hash triggers on for one of my build systems, did a kernel compile, started up evolution, did some web surfing, and what I found was that there were a lot of kmallocs, in that case 30 million kmallocs, but the interesting thing was that all those kmallocs were funneled into only 538 call chains, which I was expecting a lot more, but maybe I shouldn't be, maybe I just misinformed, but that seemed like a significant thing, that only 538 call chains used for a heavily used system, whereas just through start kernel, things that normally would never be picked up, I have 5 times that many. So as you can see here, there's only 11,000 kmallocs, which means that the amount of memory isn't really probably that significant compared to 30 million, but in call chain terms, it is significant, I think. And anyway, even if it's not important, I thought it was interesting, and I pass it along. This is just a couple of quick slides about the hash triggers. I don't want to spend much time on them. I just put them in here in case people decide to try microYocto out, try the hash triggers, that at least the current status of them would be on the slides here. The hash triggers, the normal hash triggers work just fine. I submitted an initial patch set to kmalloc, and got a decent response. And I'll probably pretty soon try to refine those, make them actually mergeable. But the early hash triggers are a complete hack. I mean, and actually kind of crazy. And I wouldn't. Yeah, they work. So I wouldn't steer you away from them if you're really interested. But it's kind of crazy. We have to do to use them. And the reason it's like that is because to really do this right, we need to have ftrace available a lot sooner. And that, when I looked at it, it seemed like a bigger job than I wanted to do at the time just to get the data. And it's definitely something I'd be interested in doing some work on later. But anyway, that's the way, the reason the early hash triggers are kind of funky. The big restriction there is you can only do one at a time, and then in order to read the data that's there, you have to actually set another hash trigger to set it again to read the data. And here's just concretely what that means. Up here is the kernel command line that actually sets the early hash trigger. You can only do one of them. And then in order to get the data, that early data, you need to actually wait till for the system to boot up and then do a regular set a hash trigger. And then when you cat the trigger, then you get two hash tables, essentially an early one and the regular one. So I don't want to go into more into that, just in case anyone's interested in looking at it. Be aware of this. So anyway, that's pretty much the status of microYocto as it is. I'm gonna, in a couple slides, I'll go through how you can actually build and boot microYocto, but just as a little bit of background context, for that, I'll have a couple slides on what Yocto is, in case you don't know what it is, and the Yocto kernel. So Yocto is a build system, and essentially it'll build a custom system for you. That just means a kernel and a file system. What goes into that build process are recipes. That essentially tells the system what to build and how to build it. And what comes out of that are packages, RPM packages, standard packages that you know, IPK. And then once all the packages are generated, the final step is to assemble those into an image that you can then boot, a bootable image. So the key takeaway about Yocto, really in a nutshell, is it just essentially captures a set of code and configuration used to build a particular system, just as I've done with the microYocto. And then just a word about the kernel. Since that's kind of where the work has so far been focused, and probably where people would be interested in tweaking more than anything else. The Yocto kernel it's not it's just an upstream kernel. It packages it a little differently, and that's all. It's an upstream kernel plus machine-specific patches, and those are contained in a branch called the machine branch. And then there's another branch in the repo called the meta branch, and that branch just doesn't contain kernel code. It contains essentially configuration fragments, fragments of configuration that can be easily toggled on and off in a recipe. And the recipe is actually where you actually toggle those off. Just go and edit your recipe and toggle those on and off, and then rebuild, and then your kernel that comes out of that is the kernel with those fragments either enabled or disabled. But in the end, those things combined together end up with just a regular kernel source tree that you're all used to dealing with, and a .config that everybody understands, just a monolithic .config. And you can actually go in the build system and find those two bits, the things that are finally actually built to create the final image. And so just to kind of point out that there's no magic behind it, it's just a different packaging. And here's an example of, a concrete example of what that looks like. Again, the config, using config proc min enable. These are the config options that essentially are part of make up the procmin enable fragment. Here's the new one that I added, and then I turn config procfs off because I'm using the minimal version. So that's in the meta branch. And then the machine branch, this is the name of the machine branch, standard micro Galileo. This is the actual code that I added to create that config procfsmin config item. And then finally, here's the in the kernel recipe, which is this Yocto micro 3.14 bb append, which is a sort of a extension for appending a kernel recipe to turn that config item on. All I have to do is add a line like this: kernel features append, and then I have and then add my config item. So that the kernel recipe I just talked about, and as well as everything else to do with microYocto as it currently exists, is in a directory called metagalileo. It's an open embedded layer that contains a whole bunch of recipes in kernel and LWIP stuff that I mentioned before, a bunch of other things. So if you want to actually run and build microYocto on your Galileo board, the only thing you really need to do is go grab this README file in metagalileo, and on the last slide I'll have a pointer to where that actually is. And what the README will tell you essentially these steps: clone Galileo, which will just, all that does is clone a couple of repos that contain Pocky and Galileo in the kernel. And then to actually build the image, you do bitbake image micro. That'll turn for a while and end up with image micro image, a bootable image. To actually boot it on SD card, then you need to run it through this wick step, and then you'll have an image that you can then DD onto your SD card and then stick into your Galileo and then run it. And once you're booted up, this is a IP address that you'll get. It's a static IP address. You can SSH in, root with no password, and at that point you'll have access to the shell. And alternatively, you can also play around with the web server. There is the URL is up there. If you look at the slide, you can find it there. But the idea behind that the idea behind the web server is that what's there allows you to cat files, read file, to cat directories, read files, write to files, and it's meant to be sort of a proof of not proof, but just some basic functionality in case you don't have a shell, as some of the systems probably maybe won't. Okay, so as far as the future goes, we plan to do a lot more cutting, just like I've described. Then there's XIP kernel, ARM and Blackfin. I already have something like this, but what I'm talking about here is for x86. There's someone on my team that's actually working on XIP kernel. And execute in place kernel essentially means a kernel that can be executed in place in the flash where it sits, instead of being brought into RAM and taking up all that RAM. And obviously if we can do that, then we don't have to worry about all the penny pinching and all the static memory that we've been doing for the reducing static memory. The question there though is what's performance going to be like? So we should know that pretty soon. And then as far as microYocto itself goes, just making things easier to use. Right now, what I have in there is a whole bunch of groupings of things that I use to turn tracing on, to turn tracing off, to create a non-networking version, etc. And obviously, I need to do that the right way, which is to create some features to do that. And then another area where I need to do a little bit of work is make it easy to create single-purpose images. Basically, the user has an application that they want. The only application that's ever going to run on the system. Make that easy to do as a init process, for instance. And then finally, something I'm personally interested in is what I call trace-guided optimization. The sendfile, that sendfile example that I mentioned earlier is just sort of along the lines of what I want to do. I think what I'm interested in doing is going a lot further with that. Essentially, if you assume that the system is a completely closed system, single purpose, you know everything that will ever happen on that system, you trace everything, and essentially automate the whole process of tracing and removing any code that was never used, because why have it there if it's never going to be called? So that seems to me that would be the way to get to the minimum, the very minimum size that you could ever have for a system. So I'll hope to work on something like that in the future. And then I want to, that's pretty much all I had as far as content, but I want to thank a few people in particular that contributed code and comments, etc., useful information. Andy Queen, Alan Cox, and Josh Triplett. And that's pretty much all I had. I just wanted to point out, here's the code. If you just do this command, wget command here, you'll get the README, and then the README will also tell you how to get the rest of it bootstrapped, and essentially that's all you need is that one line there. So that's pretty much all I had, and if there are questions, I'll be happy to take questions. Yeah, it's. Oh yeah, he's saying, you know, the trace-guided optimization that I mentioned. It sounds great, but how practical is it really to do that if when you consider that you have to cover every single error path as well? I mean, you have to consider every possibility every possibility that could ever happen in the system, including error paths. And I don't know the answer. I'm just it's a research topic, I guess. But
so I've done a little bit of this stuff. There actually are some tools that will also do static analysis. So I did some stuff for Sony where we scanned the object files that were going to run in user space and found all the system calls, and then eliminated all unused system calls. So additionally there, and then MontaVista used to have a libopt tool that could shrink down the libraries. So there are some static things you can do, but I think the tracing is also interesting. So.
Right.
Have you tried to do the profiling using the simulator? Get the profiling from the simulator?
No, I haven't yet. She's asking, have I tried using a simulator to do the same thing? For instance, tracing all the function calls. No, I haven't done that, but it's in. We actually have. In the description of this talk, I mentioned using simulation, and I actually didn't get to that. But we do. You know, we actually don't have hardware that'll actually run this this tight of a memory system. So the next, but you know, we do. There are simulations that will allow us to do that, I think. But yeah, that's the next step. I just haven't gotten there yet. Anybody else?
So I have a question about the general approach. So one of the ways is to start the options from Linux and start tuning things down. When I started to do it at some point, I realized that the best configuration of the devices would have enough memory much to sustain, having not tuned version of the Linux with the normal devices. Do you think it would make more sense to actually have a subsystem where you would, for example, do all the compression and the system compression on the lower level, the storage itself, and compress, and the RAM is compressed, so you really actually don't have to do all this stuff. Because by removing, the line, but removing from the application side, and it's always a kind of actually do very custom applications in LWIP, etc., etc. And I noticed that if you want to try to have more and more higher level controls that you can run, multiple layers or stuff like that. And it's not uncomfortable to see this stuff in some very advantages in that system or anything like that. I don't think it's anything that compares to because it's all like HTTP sender and stuff like that. So it's longer, more in line as maybe you from the log when you actually play more the sound, lower level.
Not anything that I know of in particular at Intel, but I'm sure there are. But yeah, I mean, I guess it's kind of a moving target. You know, I sort of, picking a system 1.6 megabytes is kind of arbitrary, and the main reason is like, an order of magnitude less than 16, you're typically the smallest. So at some point, say, well, why not 1.16? I don't know. It's at some point, you can do a lot of, you can move things to hardware, but at some, you also want to be able to have a system that is super tiny without resorting to hardware.
It's always a problem if you want to run the current generation device.
Right. Yeah.
So
yeah. It's not just that drives the requirement of low code science. Applications are operating on satellites in low Earth orbit, where you only have applications, 10 minutes a day, 90% of the board. And so, when you code updates to kernel updates, you want to have really small compact code. So it's not just the hardware, but also hardware communicating with the code that updates that drive the requirement.
Anything else? Okay, well, thanks for coming.